Swayam Prabha. Digital India. Educated India.
A warm welcome to the 14th lecture on the subject of discrete time signal processing and its applications. This lecture will continue with where we left in the previous lecture, namely on the properties of the Z transform. We had introduced the Z transform in the previous lecture and we had started looking at some of its properties. I would like to recall a couple of points from the previous lecture before we proceed to say more about the Z transform and its properties. We had looked at the expression for the Z transform. Let us recapitulate that. So, if you have a sequence xn, then we said its Z transform is given by summation over all n, all integer n I mean, xn z raised to the power minus n. And this always has a region of convergence. Or ROC as it is often called for short. Now, the region of convergence is always a region between two concentric circles with the circles centered at the origin. And we said that one of the concentric circles could possibly have radius 0 and the other one could possibly have radius infinity, right. So, 0 and infinity are also possible radii. It was also a point that needed to be addressed to look at whether the boundaries are included in the region of convergence, right. The boundaries may or may not be included and that needs to be checked in each case individually. One guideline is if there is a singularity on the boundary, a point where that quantity diverges, then of course that boundary cannot be included in the region of convergence, right. So, these are about the Z transform in general and its definition and its contents. A Z transform always has an expression with a region of convergence. Yes, there is a question.
We said that Z is equal to R into e raised to j omega.
Yes.
Does R have any physical significance?
Oh, so that is a good question. It says, we had said, all right, so let us come to that. We had said that Z is of the form R e raised to the power j omega. So, the question is omega seems to have a physical significance. And that physical significance is the angular, normalized angular frequency, isn't it? However, the question is, does R have a physical significance? R does indeed have a physical significance. There are two ways of understanding R. One way is, a formal way. That is, it is the rate at which the exponential should multiply that sequence so as to bring the Z transform into convergence. That is a formal way of understanding R, right. So, if you look at it, xz is equal to summation over all n, n from minus to plus infinity, xn, and now let us write this in terms of R and omega. So, e raised to the power minus j omega n and R raised to the power minus n. So, R is the exponential parameter in a way, exponential or curtailing parameter, if you may call it that. Essentially, it ensures that the sequence converges on multiplication by this exponential. So, R is in some sense the rate at which the exponential must grow to capture the sequence, or another way of looking at it is r to the power minus n is the exponential that must capture the sequence to bring it into convergence. right? That is the way to understand it. If we speak informal language, if we recall the analogy of the tiger that I gave last time, R is the size or the strength of the cage that you need to encapsulate the tiger, right. So, you have this sequence which refuses to converge, which you cannot train, for whom you cannot find a frequency response. So, you need R to capture it, to tame it, so that a frequency response exists. That is the physical significance of R. So, that is a good question. Any other questions from the previous lecture? Yes, there is a question. Yes. Okay. Okay. So, the question is, can we view the Z transform as the discrete time Fourier transform of a sequence? Can you think of the Z transform as indicating the frequency content of some other sequence? Yes, indeed, of course. If you look at it, in its region of convergence, xz, which is summation n going from minus to plus infinity x n r raised to the power minus n times e raised to the power minus j omega n, is the dtft of x n r raised to the power minus n. So, in fact, it is the discrete time Fourier transform, or in other words, it indicates the frequency content in a suitably weighted sequence xn, or xn weighted by an exponential. The exponential should strongly, or it should be strong enough, the exponential should be quick enough to capture the growth of xn, so that this discrete time Fourier transform converges. So, in a way, the Z transform on any particular circle in the region of convergence, take any circle centered at the origin lying entirely in the region of convergence. On that circle, the Z transform is essentially the sequence, is the discrete time Fourier transform of the sequence given by xn multiplied by r raised to the power minus n, where r is the radius of that circle. That is the way to understand it. Yes. Any other questions? Any other questions before we proceed? Yes, no other questions, none at all. All right, so then we will proceed to look at a few more properties of the Z transform. Now, we had seen some properties. We had seen that the Z transform is linear. We had seen that it is linear as an operator. Secondly, we had seen that the Z transform has a property of delay, the delay property or the shift property, isn't it? That is, if you shift a sequence by d, then the Z transform gets multiplied by z to the power minus d. Of course, we had talked about the region of convergence. We also saw what happens when we differentiate. This was what we were looking at last time. So, we saw that if you differentiated the Z transform, right. So, if you have dxz dz and multiply this by minus z, it is the Z transform of n times xn. That is interesting. And we also looked at the region of convergence. In each case, we had seen the region of convergence, right. We saw that normally a Z transform is analytic in its region of convergence. In fact, we are going to restrict ourselves to that class of Z transforms. So, the same region of convergence would hold for this derivative, save for the boundaries. The boundaries need to be checked, right. Now, we look at a very important property of the Z transform, namely the property of convolution. That is the real value of the Z transform. So, what happens when we convolve two sequences? So, let xn have a Z transform xz with a region of convergence Rx, and let Hn have a Z transform Hz with a region of convergence Rh. We ask what is the Z transform of the convolution of x with H. Now, you see principle that we will use to arrive at the answer is very similar to what we did in the case of the discrete time Fourier transform. There is no fundamental difference. The only thing is that we have to remember that Z must lie, you see, in principle. Here, let us take a Z to lie in the region of convergence of both, namely the intersection of the regions of convergence. Now, there are tricky issues here. What happens if the intersection is null? Can you still convolve? Well, we will not answer these questions now. They are tricky ones, but for the moment, let us take a situation where there is a non-null intersection of the region of convergence, and let us pick a Z from that intersection of the regions of convergence of R and Rx and Rh. So, let us say for the moment, I am saying for the moment, assume that Rx intersection Rh is not null, is not empty. Pick a Z from that intersection and use that Z in the discussion that follows, or use any of those Z's in the discussion that follows. Now, let us look at the Z transform. Let us call X convolved with H, let us call it Y. So, of course, we need to find out the Z transform of Y. So, Yz is of course summation n going from minus to plus infinity, Yn Z raised to the power minus n, and we have picked a Z chosen suitably, chosen in Rx intersection Rh, as we have said. Now, expand Yn. So, you have Yn is summation over all k integer xk h n minus k, whereupon we have Yz is given by summation n over all integer summation k over all the integers xk h n minus k times z raised to the power minus n. And of course, we use the same strategy as before. We put n minus k equal to another variable m. And now, instead of n and k, we go to k and m. So, of course, k is as it is, k runs over, you see k and n independently run over all the integers. So, for a fixed k, n runs over all the integers. Now, if n and k independently run over all the integers, then for a fixed k, m would also run over all the integers independent of k, right. And therefore, we could rewrite this summation here as summation k over all the integers, summation m over all the integers, and we have xk hm, and n is of course k plus m. That becomes summation of, I am not writing the limits every time, they are understood, hm z raised to the power minus k z raised to the power minus m. And now we notice something very interesting. There are terms that depend only on k, there are terms that depend only on m. So, we can act summation m on the terms that depend only on m, and that leaves us with, so you see, I mean, what I am saying is, we could take this term and operate the summation on m on them, that gives us a quantity independent of k. So, that leads us to summation k over all the integers x k z raised to the power minus k in bracket summation over all m h m z raised to the power minus m, and note that this is essentially h z, and h z is of course independent of k. So, I can draw h z outside the summation because it is independent of k, and that leaves me with this, but then this happens to be x z, and therefore, we have a product of h z and x z. That is very interesting. So, y z is clearly x z h z. So, in other words, this is a very important theorem. It says that convolution in the natural domain leads to multiplication in the z domain. This is not surprising because in particular if the unit circle or mod z equal to 1 or r equal to 1 is included in the regions of convergence of both, or at least definitely of y z, then you would find that this boils down to the specific property of the discrete time Fourier transform. Namely, when I convolve two sequences, if each of them has a discrete time Fourier transform, their convolution would also have a discrete time Fourier transform given by the product of these. Now, you see, we can also give this an interpretation. What we are saying is that if you have a linear shift invariant system, with impulse response h n, and if you have a sequence x n, we are saying that if you see as such x n and h n may not have discrete time Fourier transforms, but again you could encapsulate these tigers in a cage, multiply them by suitable exponentials. So, you could multiply x n, multiply each of x n and h n by a suitable r raised to the power minus n. And now you can use the property of the discrete time Fourier transform. So, you could now treat x, you see the beauty is that now the same LSI system, but now the impulse response should be viewed as h n r raised to the power minus n, and here we have x n r raised to the power minus n given as the input. The beauty is that you would get y, instead of y n you would get y n r raised to the power minus n, or in other words, if you took the dTft of this, dTft of x n r raised to the power minus n multiplied by dTft of h n r raised to the power minus n is equal to dTft of y n r raised to the power minus n. So, you use the same property. What we are saying is you use the same property of the discrete time Fourier transform, but on a suitably treated or in a suitably tamed sequence or suitably tamed input and impulse response, tamed by r raised to the power minus n. That is what we are saying effectively. Of course, in some cases you may in fact view this not as a taming, but also as a license. So, for example, if you look at it, suppose we take x n equal to half raised to the power of n u n, and h n equal to 1/3 raised to the power of n u n, we can easily obtain their z transforms. It is very easy to see that x z is 1 by 1 minus half z inverse with mod z greater than half, and similarly h z is 1 by 1 minus 1/3 z inverse with mod z greater than 1/3. Very easy to see. So, of course, if you take the convolution, if this h n happens to be the impulse response, and of course, you note that an LSI system with this impulse response h n would be stable, because this sequence is easily seen to be absolutely summable. In fact, you can find its absolute sum. But that apart, the sequence gives us a stable LSI system for the impulse response, and x convolved with h, which is y, has the z transform y z given by x z h z, which is 1 by 1 minus half z inverse into 1 minus 1/3 z inverse. And of course, now the region of convergence is indeed the intersection of the two regions of convergence. So, mod z must be greater than half, mod z must be greater than 1/3. So, in total mod z must be greater than half, because that is the intersection. Now, mod z greater than half is like a license. I told you, we have been talking about encapsulating or taming the sequence, but here mod z needs only to be greater than half. You can take, for example, mod z equal to 3/4. In fact, you can take z equal to 3/4 if you like. Now, 3/4 raised to the power minus n is actually an exponentially growing sequence. It is 4 by 3 raised to the power of n. So, in a way you are saying, even if you multiply x n and h n by an exponentially growing sequence and take their discrete time Fourier transforms, yet you could apply the property that we did a couple of points a couple of minutes ago. What I meant was, here we had x n r raised to the power minus n applied to h n r raised to the power minus n, giving you y n r raised to the power minus n. So, here r could be a quantity less than 1, r could be 3 by 4 in this example, which means it is actually an exponentially growing sequence. So, there is a license also. There is a bit of a license to allow the sequence to grow, but still you can encapsulate, you can allow it to apply the discrete time Fourier transform property. Of course, this is because the sequence itself is exponentially, both of the sequences are exponentially decaying. So, if the exponential growth is slower than this decay, then on and on this leads to a decay, and therefore, you can have some license. That is what we are saying in effect. Anyway, so much so for license and taming. Now, let us get back to this example of y z here. You see, here you have a product of two z transforms, and the beauty is this product of the two z transforms can also be expressed as a linear combination of the two z transforms. So, suppose I wish to find the sequence y n from here, how would I go about doing it? Now, one would use what is called a partial fraction expansion. How would we obtain y n? Decompose y z. Now, y z, which is 1 by 1 minus half z inverse, 1 minus 1/3 z inverse, can be decomposed as something on 1 minus half z inverse and something upon 1 minus 1/3 z inverse. What upon each? And the idea is very simple. When I want to find this factor, I multiply y z by 1 minus half z inverse. and put z equal to half. So, essentially I am multiplying by 1 minus half z inverse and making this factor 0. So, multiply by 1 minus half z inverse, put z equal to half. So, I get 1 minus 1/3 into half inverse, that is 2. So, I have 1 by 1 minus 2 by 3. And here I would use the same idea. I would multiply this by 1 minus 1/3 z inverse and put z equal to 1/3. So, in other words, z inverse or so z equal to 1/3, that is right. So, z inverse is 3. So, there we are, 1 by 1 minus 3 by 2. Now, let us verify, indeed let us verify. What we are saying is 1 by 1 minus 2/3, that is 1 by 1/3. So, 3 by 1 minus half z inverse, and 1 minus 3 by 2, that is minus half. So, minus 2 by 1 minus 1/3 z inverse. This is very easy to combine. So, 3 minus z inverse minus 2 plus z inverse. Okay, and that indeed gives you back 1 by exactly the yz that we had. Now, what I just illustrated is what is called a method of partial fraction expansion. It is a method of expanding a rational yz in terms of factors where there are denominator terms all acquiring the value 0 only at one point in the z plane. Now, we often deal with this class of z transforms. Let us introduce this class of z transforms. We call them rational z transforms. Rational z transforms are z transforms of the form finite series in powers of z divided by finite series in powers of z. There is a numerator and denominator, each of which are a finite series in powers of z, not infinite. And of course, the word rational comes actually from the idea of rationality in the integers. Let us take a rational number as we understand it for integers. 116.72 divided by 21.68 is a rational number. In fact, even if I put 689, it will be a rational number. Why is this a rational number? Because I can multiply the numerator and denominator by 1000. And that leads me to 116720 divided by 21689, which is a ratio of integers. So, it is rational. Now, let us expand this quantity 116.72 by 21.689 in terms of powers of 10. So, in fact, we can see that 116.72 divided by 21.689 can be rewritten as 10 raised to the 2 into 1 plus 10 raised to the 1 into 1 plus 10 raised to the 0 into 6 plus 10 raised to the minus 1 into 7 plus 10 raised to the minus 2 into 2 divided by similarly for the denominator. can easily write the denominator as 2 into 10 raised to the power 1 plus 1 into 10 raised to 0 plus 6 into 10 raised to minus 1 plus 8 into 10 raised to minus 2 plus 9 into 10 raised to minus 3. So, essentially a rational number is a finite series in the base. Here the base is 10. Of course, you could write it, you could write the numbers to the base 8, or you could write the numbers to the base 3, or you could write it in binary, whatever you like. So, what is a rational number? Rational number is a ratio of two series, each of which is finite in the base with respect to which those numbers are written. The same idea is being used here, except that the base is an indeterminate z. So, it is a generalization of the idea of rationality as understood from the context of integers or numbers. Now, this generalization does not stop there. There are certain important properties that rationals have, and systems whose impulse response has a rational Z transform are called rational systems. So, now let us define rational systems. Rational, and of course, the word rational system immediately refers to an LSI system, otherwise it has no meaning. So, rational LSI system is an LSI system whose impulse response has a rational Z transform. And of course, the LSI system that we saw a few minutes ago is an example. Rational systems are very important. In fact, almost all through this course in the sequel, we shall be talking about rational systems. We shall of course take examples of irrational systems, but we shall actually design only rational systems. There is a good reason for that. To date, it is only rational systems that have a meaningful realization. What is meant by realizing a system? Realizing a system means translating a system into a hardware and or software structure, implementing a system with concrete components and operations. And of course, they must be finite in number. You can always conceive of a system that requires an infinite number of operations to implement, but that is of course of no practical significance. Unless a system can be implemented with finite resources, the system is not very useful in practice. It is only rational systems that can be implemented with finite resources as far as LSI systems go. And that is why rational systems are of such great importance and relevance to us. So, you see, the system that we saw a minute ago is indeed an example of a rational system. And now, of course, let us complete the job of inverting the Z transform for which we had set out. You see, we had set out to invert yz equal to 1 by 1 minus half Z inverse times 1 by 1 minus 1/3 Z inverse. And we had seen that this is essentially 3 by 1 minus half Z inverse minus 2 by 1 minus 1/3 Z inverse. And of course, the region of convergence is mod Z greater than half. And now, you see, this is a sum of two Z transforms. Take this term, when mod Z is greater than half, 3 by 1 minus half Z inverse from the linearity of the Z transform must correspond to the sequence 3 times half to the power of n un. And since mod Z is greater than half, mod Z is of course greater than 1/3. So, for this sequence too, with this expression with mod Z greater than half can also be thought of as the same expression with mod Z greater than 1/3. Mod Z greater than 1/3 is of course true. Yes. So, therefore, the inverse Z or the inverse, the sequence corresponding to this, or we might call it the inverse Z transform, of yz, which is yn, is 3 times half raised to the power of n un minus 2 into 1/3 raised to the power of n un from the linearity of the Z transform. Now, this example brings a very important point to light. You notice that in this example, the output Z transform is the product, it is the convolution of the sequences xn and hn. It is a convolution of the input with the impulse response, but it also happens to be a linear combination of the input and the impulse response. This is something very peculiar to rational Z transforms. In fact, you also see why this happens. You notice that we inverted the Z transform by decomposing into partial fractions. When you decompose into partial fractions, what you are saying is each of the terms in the denominator give rise to one term in the partial fraction expansion, and therefore, a product of various terms in the denominator leads to a sum of the same or a linear combination of the same terms. Now, we introduce one more idea here. In a rational Z transform, denominator equal to 0 gives us what are called the poles of the system. We will explain in a minute why they are called the poles. Well, I should not call it the system necessarily, system or sequence, as the case may be. We say system if that rational Z transform is the Z transform of the impulse response, and we say sequence if we are talking about the Z transform of a sequence. Now, the numerator equal to 0 gives us the zeros of the system or the sequence, and we will explain in a minute why this nomenclature. In fact, let us visualize the magnitude of the Z transform. You see, the magnitude of the Z transform is always non-negative. So, you can visualize the magnitude of the Z transform plotted on the Z plane. So, I draw a 3-dimensional or a seemingly pseudo 3-dimensional picture here. I have the Z plane and the vertical. Remember, the vertical is only in one direction, so it is mod Hz. Now, wherever there is a 0, you can visualize mod Hz now as a tent on this Z plane. That is easy to visualize, because it's, you see, a tent means it must be only, you can't have a tent under the ground. So, a tent must be only above the surface, and that is true because mod Hz is non-negative. So, this tent, what happens to the tent? Wherever there is a 0, the tent joins the ground at that point. What happens to the tent? Wherever there is a pole, the tent rises upwards, you see, goes towards infinity. That is why it is called a pole. The point where the denominator becomes 0 leads to the tent reaching the sky by virtue of a pole, and the point where the numerator equal to 0, the tent goes and touches the ground. Okay, so that is why this terminology, poles and zeros. Anyway, the poles are very important. If you have a linear shift invariant system, Now we have defined what a rational system is. So, in a rational system, we call the poles the front stage actors and the zeros the kingmakers or backstage manipulators. You see, when you make a partial fraction expansion of a rational Z transform, it is the poles which tell you what terms you should have. What do the zeros do? The zeros influence the coefficients of these terms. So, zeros do not explicitly figure in the partial fraction expansion, they implicitly figure, they are kingmakers. They say, who should go forward, who should go, say, backstage. The actual actors which you see on front stage are the poles. The poles are what determine what kind of response that system has, impulse response. And in fact, if you look at the poles of the input and the poles of the system, together they tell you the poles of the output. What role do the zeros play? The zeros determine how important, how unimportant each pole is, because they influence the terms, the numerators of the partial fraction expansion. Is that right? So, zeros do not explicitly figure in the nature of the response, but the zeros are important. Just as in a drama, the front stage is important, the actors on the stage are important, as are all the people manipulating. See, if they don't, if the people at backstage suddenly turn the lights off, the actors are of no good. That is what the zeros do. Sometimes the zeros kill one of the poles, they do that, turn the lights off on that pole. So, the zeros are backstage manipulators. Anyway, the zeros and poles together determine the nature, and in fact, here we can see that, you see, when you have an input and an impulse response, both of which have rational Z transforms, the poles of the input and the poles of the Z of the impulse response together determine the poles of the output. That is easy to see, because in fact, the poles of the output are a union of the poles of the input and the poles of the impulse response. That is very easy to see, because the Z transform of the output is the product of the Z transform of the input and the Z transform of the impulse response, and therefore, it has to be, the poles have to be the union of the two. Of course, but the zeros can play a role, they might come in, as I said, turn the lights off, they might cancel some of the poles, that can happen. If they do not cancel, all the poles will be there. And that also tells us, now when you do a partial fraction expansion, it also tells us that the output is going to have terms which come from the input and which come from the impulse response. In a way, in a rational situation, in a situation where both the input and the impulse response are rational, the output can also be thought of in some sense broadly, don't take this literally, but broadly as a linear combination of the input and the impulse response. So, convolution also leads to a linear combination broadly. Do not take this literally. We shall see more of this in the next lecture.